เ Hi everybody, welcome back to Chem 140. There is someone here that wants to say hello. Let's see if we can get her on the mic. Are you gonna say anything? Hello? Say hello. No, she just wants to be right here and rub my shoulder, I guess. Oh, and now she saw the other cat, so she's gonna go chase him. What are we doing today? I don't even know. Oh yeah, we're gonna finish Unit 9. What do we have for agenda items? There's a quiz due tonight that looks like it's for Unit 7 and 8. That's quiz number 4. Make sure that you get that done with a deadline. Tomorrow that assignment will close at 11:59 p.m. So do your thing by then, and everything should be good. Yesterday we left off talking about the octet rule, and I believe somebody had a question about, hey, what do we do for transition metals? And I forgot that this slide exists. This is the previous slide. I actually went backwards here. What the slide is talking about is that the octet rule that we have spent about an hour or two going over how to build an ion to get to the octet rule only works for the elements in groups 1 through 8A. And again, so those are groups, if you're using the IUPAC numbering scheme, that's 1, 2, and 13 through 18. Now, that's only the octet rule. That doesn't have anything to do with making ions in general. You can make any ion into any element, or you can make any element into any ion that you want to by simply adjusting its number of electrons. So, for example, for iron, you can remove 2 electrons to make iron 2+, or you can remove 3 electrons to make iron 3+, and those are actually very common. But they don't follow the octet rule. They play around with some other patterns that we're going to talk about in Chem 161 when we look at electron configurations. And as a result, we're not going to draw Lewis symbols for those. Okay, so the only Lewis symbols that I'm going to ask you to draw will be for elements that are in groups 1 through 8A. So no Lewis symbols for transition metals or intertransition metals. It's not something that's useful to do because it doesn't really model anything helpful. We're going to use a different model later on to explain those phenomena. So you can see some examples of some ions that I will give you at the bottom here. So when we start working problems with these today, what we're going to do is I'm going to either give you the ion with a charge, or I'm going to give you enough information so that you can calculate the ion's charge by using the assumption that all the charges add to 0, which we're going to talk about right now. All right, so what we're going to do is we're going to construct ionic compounds using all of this information. So we know how to make ions. They follow the octet rule. We know how to count valence electrons so that we can figure out how many we need to change to get to the octet rule. So if I start with 5 electrons, I want to get to 8, so I'll add 3, and that gives me an ion with a -3 charge. Hopefully we remember how to do that from yesterday. Because once we have done that, now we can make ionic compounds. Now, ionic compounds form on the very simple premise that opposite charges attract to each other. So if I have something that's positively charged, like, say, sodium, and something that's negatively charged, like chlorine, they will attract and form an ionic bond. And then that's it, you're done. Hooray, the charges have attracted to each other. Now, if I do something like this, and these attract, I still have an extra positively charged effect. And what that means is that the influence of the positive charge could extend to another minus, right? I have +2, but that's only attracted 1 negative to it. So I could attract a second negative to this to form my ionic bond. And then this would be complete, and we wouldn't need to have that there. Yeah, it was a pretty good heart, wasn't it? So the result that we are going to observe here is that whenever we make an ionic compound, the sum of charges will equal 0. And the reason for this is if we didn't equal 0, then the whole thing would remain charged and it would attract other things to it, right? So for instance, let me clear all this out right here. If I had these two things together, oops, that's not a pen, that's the laser pointer. If I had these two things together, would the ionic compound be complete? Well, no, I have extra positive, right? Well, so I'll put another 2 negative on here. Would it be complete now? Well, now I have too many negatives, so I have to put more positive in there. And so on and so forth. So this ionic compound will get bigger and bigger and bigger until I have balanced out all the charge, which it turns out if you do this, then we're all good. Oops, there wouldn't be one here. I'm just drawing lines all over the place that don't really make much sense in the context of ionic bonding here. But the total charge for this system would be, well, there's 6 negatives and there's 6 positives, sums up to 0. And so we're just going to keep adding ions until everything neutralizes. So there's our simple ionic bond shown on the screen here. And do note that the positive and the negative can be different numbers. Now, this diagram is extremely simplified. I've shown you what the ionic lattice looks like in a previous lecture. I think it was back in like Unit 4 or something. We were just starting to talk about matter. Or I guess that'd be Unit 6, something like that. We'll see that again. Oh, right here. In an ionic compound, ions will repeat over and over and over in patterns. And that pattern is called the formula unit. Now that remember, the formula unit's total charge, like we just said on the previous page, is 0. In other words, if we can make a formula unit with charge 0 and just paste it over and over and over and over and over again, we can create the ionic lattice, which is what we observe. So in other words, this circled unit that I have right here, I'm just going to copy and paste that over and over and over. Done. Bam, I've made my ionic compound. Now, that's a gross oversimplification. In reality, we're actually pasting a 3-dimensional volume that has the equivalence of that positive and that negative. But that's a little too complicated for now. We might talk about that in 162 a little bit more when we look at the unit cell. But for now, just think of it as the simplest copy-paste that you can do. And as you increase the charges on things, these lattices look more complex. So you would only have half as many magnesiums as you do sodiums in here if you were looking at magnesium chloride, because magnesium is +2, for example. And so that would change the structure. And so there are all sorts of different lattices out there that you can look at. And you just repeat the simplest formula, and that is the formula unit. Now, you will probably want to recall earlier when we talked about molecules. Is an ionic compound a molecule? Well, we said that molecules were independent entities, right? So if I have a water molecule and I have a second water molecule, they're not touching each other or hooked together. I could physically divide them with, like, say, a really thin sheet of glass or my hand or something like that. There is a region of space between them. But for ionic compounds, that's not true. All the ions are crammed all up next to each other. Their electron clouds touch. So there is no molecule in an ionic compound. You just have a lattice of repeating formula units. Okay? Be careful with the terminology, because I know everybody likes to throw molecule around a lot, but there is no ionic molecule. Make sure that you understand what a formula unit is, so that you don't accidentally break that distinction, we'll say. All right, so that's the gist of how our ionic bonds are forming, is the opposite charges that are attracting. Now, in our ionic compound, charges do propagate in all directions, which is why this chloride on the corner here is touching only positives. And if I were to look at, say, this sodium right here, the sodium is touching only negatives. Now you might think to yourself, wait a second, that's only a positive 1. If I have 5 or 6 negative things around it, how the heck does that charge balance out? Well, it turns out every other ion is also touching 5 or 6 other things. And so they're all sharing their charge in all directions with everyone. Now, conceptually, that's hard to visualize until we talk about the unit cell in 162. So if you prefer to think about ionic compounds as just formula units that stick together, that you copy and paste, totally fine. This is an intro class. The model I give you just has to sort of get you there. It doesn't have to be perfect, right? All right, so we know that if we have a positive and a negative, they would attract to form, eventually, a lattice. But what happens if you do this? I don't know why it disappeared. What happens if you do this? If I were to react regular old sodium and then chlorine together, I'm going to just take half of my Cl2. Chlorine arrives as Cl2 because they're bonded in pairs. But if I added these to a container, what would happen? Would they actually react? Because there's no charges present, right? Now, it turns out that they will react, but they need a little bit of encouragement. And we're going to see that here. So give me a sec to call this up here. Oh, I don't need to do that. What am I doing? All right, so this is Lonnie. I believe Lonnie teaches at UC Berkeley. And his picture, oh, that's creepy as hell, right? Like, that's exactly what we wanted, is just his eye floating around there. I don't know if that's much better, to be honest, but okay. So I'm going to talk over Lonnie's lab here as he does this experiment. But what Lonnie's going to do, Lonnie's going to react chlorine gas, which is kind of hard to see here. Let me actually pause the video. I'm going to zoom this in. Can you see that in the cylinder, kind of right here, it looks a little bit yellow, right? That's chlorine gas. Chlorine gas is this very pale yellow gas that is extremely corrosive and reactive. And so there is definitely a gas in here. It is hard for us to see, but I will ascertain that it actually is in there. And what Lonnie's going to do is he's going to remove the gas valve after turning it off and then sealing the container. Now, chlorine gas is very dangerous. Why is he doing this without a respirator? Well, it turns out right here in the bottom where you can't really see because of the time bar, that's a fume hood. There's a giant vent pulling the gas down, and he's totally safe. So the next thing that he's going to do is he's going to take a chunk of sodium metal out of this bin, I guess we'll say, that's just full of mineral oil. And he's going to rinse off that mineral oil in hexane, because hexane's really volatile. It'll burn right off. But the oil is kind of obnoxious to deal with, so he's going to rinse the oil off there. Then he's going to take this and put it in a ladle. And he's going to put the ladle in the Bunsen burner on the left here. So you can see this Bunsen burner. You're going to work with a Bunsen burner in the lab this week, so you'll get to see this in action. It's basically a natural gas flame. And he's going to heat this up until it starts to glow orange. This color is going to be relevant to you for the lab because we're going to ignite things with sodium in them, and they'll turn more or less this color. This is actually a little bit darker than I think it normally appears. I think sodium's a little more yellow. But elements tend to burn, especially if they're ionic elements. They burn with a specific color, and so that is something that we'll talk about on Wednesday. Now what Lonnie's going to do is he's going to take the hot sodium and put it into the chlorine gas, and something will happen. What he's done here is he's just provided enough energy for the reaction to start. And once the reaction starts, it will continue on its own. Think of it like striking a match. In order for your match to start burning, you have to strike it against a rough or corrugated surface or something like that. And then you can use it to light like firewood on fire, and then that goes on its own. Same thing is happening here. The sodium metal is now reacting with the chlorine gas, and you could see that the container's gotten really murky. You can't really see what's inside anymore. You could see like what looks like a gas coming out. That's actually table salt, believe it or not. Table salt in the gas phase, which, I don't know about you, but that's kind of creepy as hell to think about. When I look at my table salt, I don't think about gas phase. I'm going to pause that real quick, and I got to back up a little bit. We're going to bring his ladle up here. Look how hot the ladle got. We'll zoom that in if you want to see that. So there's the ladle right there. It got red hot. And the reason that it was red hot is because this reaction released a ton of energy. Just like when you light a match, it flares up at first, and it gets real bright, and then it starts to slowly die down as it consumes the rest of the phosphorus and sulfur and fuel that's on the match head. So the reaction generates enough energy to sustain it, and that heats up everything in the container, including the ladle. So he's going to set that down, and he's going to let this condense for, I don't know how long this would take, probably an hour or two to cool down to room temperature, at least. But he's already done this experiment before, and this is the result that you get. It looks like table salt down here, which I'll zoom in, even though you can't really see it super well. So there it is down here. Let me hit play again so that goes away. And in fact, if you were to do this experiment under conditions that were clean and safe, the results that you get would be edible. As Lonnie's going to demonstrate here, disclaimer, never eat in the laboratory. Lonnie, what are you doing? I get that you're old and will die soon, but don't put yourself at risk. That's not cool. Alright, so, oops, hold on, I gotta get OBS back on the other screen here. So, what did we see actually happen? We saw this reaction. We're going to start to get into reactions now. Ooh. So, this is what's known as an ionic compound. Oops, I can't read that because chemists usually don't live as long as other professions. Yes, that is true for the most part. Cancer gets us pretty quick. Is this why? Eating in the lab? Could be. Alright, so this type of reaction is what's known as an ionic compound formation. But also, you could describe it in many ways. So one way you could describe it is oxidation reduction. You could call it combination. There are a bunch of different terms here, but the action that occurred here is something that's called electron transfer. Now, how does this work? What if we drew a Lewis symbol for each of these elements, and we said, okay, I want to make the octet rule for both atoms. I want to form them both into ions. Is there something I can do to make that happen? And the answer is, if you move this electron over here, then sodium would go from 1 valence electron to 0, and chlorine would go from 7 valence electrons to 8. And this right here, this action, this is chemistry. Isn't it nice to know that this entire class that you've been struggling with for 6 weeks now, and there's like 74 quarters worth of this shit, has been reduced to a dot moving to another dot? That's chemistry. We're moving dots. Now, obviously, there's a lot more nuance to it, but you really can reduce chemistry to, oh, it's an electron. There it goes. That's chemistry. So in the act of putting these two things together, yeah, right? Like, doesn't that kind of suck? Like, when I started taking chemistry classes in high school because it was as close as I could get to magic. Like, my instructor did a reaction, which we'll do in 163. It's called the iodine clock. And he mixed two things together, and then after like 15 seconds, the solution just on its own went from clear and colorless to just dark purple. And I was like, that's the most fucking awesome thing I've ever seen. So I was interested in it. And then I learned this shit, and I was like, wow, I have wasted my life. No, not really, actually. That sort of realization is scripted just for your amusement, but it does kind of oversimplify things, and there is a little bit of an elegance to it, but it's also kind of like a disappointing elegance. So we're going to just shuffle this electron around. And this is going to be our goal. Can you shuffle electrons around so that everyone has an octet? And if you can, then the result that you get is the ionic compound that forms. So this is our ionic compound. Remember that the charges add to 0, so there's a positive and a negative. Because when I move this electron away, this charge forms. And when I move this electron in, this charge forms. And then those are attracted together. So this is how ionic compounds form. Specifically, this is how table salt is formed. Back when the planet was made, billions upon billions of years ago, sodium and chlorine were introduced as matter coalesce into the rocky formations and stuff, planetary stuff. I don't know the geological names for early rock. But in the atoms of that giant mass of stuff, there were sodium atoms and there were chlorine atoms. It was still really hot during the formation of the planet, so they reacted, and that's how we have so much table salt here. Would describing the reaction as exothermic be accurate? It would, actually. But exothermic and electron transfer are two different things. So what exothermic means is when you do the reaction, energy is released. And so an energy release can be observed in the form of, say, light or heat. Heat is the most common one. Sometimes you get light. But energy is released, and that energy can be absorbed by other things. So, for example, burning fire in the fireplace is an exothermic reaction because the energy in the log, or the wood, or whatever it is that you put, or the natural gas that you are burning is released, and you get it. That's why you feel warm. You put your hands next to it and you're like, oh, that feels warm. Because that energy didn't just materialize out of somewhere. It was contained within the chemicals that you are burning in your stove. Same thing happens here. So that's what exothermic means. Energy's coming out of the reaction. Most reactions are exothermic. There are some that are endothermic, where you have to put energy in to make the reaction go. All right, so to summarize, when we make ionic compounds from neutral elements, so that's these guys right here, we are going to shuffle electrons around to get octets. Should you use exothermic with observations? You can. We're not actually focusing on the energy aspect of this. Something that is exothermic is a helpful observation to make in terms of data. So you may want to do this quantitatively, or we'll do that in 162 when we talk about thermodynamics. So here's our summary. In order to make an ionic bond, you have to make the ions first. So you're going to transfer the electrons. On paper, we're going to shuffle those around. And we're going to do that until we have octets. And then once you have octets, everything comes together. I don't know why my PowerPoint does this. Once you have created octets, all the ions will become attracted to each other, and you'll create your ionic compound. Now, in red here is an important note about bonds between metals and nonmetals. In order to form an ionic bond, you have to choose an element that wants to give away its electrons, and you have to also choose an element that wants to accept electrons. So in order to form an electron transfer, you need to have one of each type, one metal and one nonmetal. Someone to give away their electrons and someone to accept them. Otherwise, you can't make an ionic bond. You might get some other type of bond. All right, so let's do some examples. So I'm going to come back to this comment here, metal first, then nonmetal. We've already talked about charge being 0, but we're going to look at these two ions here, K plus and S2 minus. So what we're going to do is we are going to go over here. Put that up there. And so what I'm going to do is I'm going to say, hey, we've already made our ions. So I'm going to draw the Lewis symbol for both of them. And so now that I have made these ions here, I want to balance their charges out. So if I look at this, and I were to combine these together to make this formula, because I have one K and one S, right? What would the total charge be? Well, it'd be positive 1 and negative 2, right? I can't have negative left over on my charge. So if I'm going to make an ionic compound out of potassium and sulfur, I'm going to need more positives to neutralize out this negative, right? So if I do this and put a second one in here, now what's my charge look like? And what's my formula look like? Well, now I have positive 2 and negative 2. Those would sum together to give you 0. So this right here that we're going to circle in purple, this is what would make our ionic compound. What would its formula be? Well, there's two Ks, and there's an S. And there's our formula, K2S. So what I've done here is I've tried to do this without drawing the electrons moving around. You can do that if you'd like, and we can show that here. Here's potassium as normal. It has 1 valence electron because it's in group 1. Here's my sulfur. Sulfur has 6 valence electrons. If I do my electron transfer, I can move this electron over here. And this potassium has an octet. It has 0 valence electrons, right? But this sulfur doesn't have an octet yet. It has 7. There's still an empty space down here. So I would need to get a second potassium here in order to do that. And once I've done that, now everything has an octet, and so I can write my formula. I use 2 potassiums and a sulfur. Whichever method helps you, use it. You can either draw out the octets as they form and shuffle the electrons around, or you can do the numerical approach if you already know what ions these elements form. Now, in some cases, this approach is the only one that you're going to be able to use. For example, if I give you something like iron 2+, I don't care that GeForce Game Ready drivers are available. That's fine. My computer's popping up like, you should download all these things. I'm like, no. If I give you something like iron 2+ or something, you can't draw a Lewis symbol for that, right? Because we just said we don't draw Lewis symbols for transition metals. They don't follow the octet rule, right? So then you have to use the strategy on the top left here. But for elements that are in groups 1 through 8A, you can do the dots if that helps you. Okay? Now, when you write the formula for a compound, and we're going to be writing a bunch of formulas here, the convention is that you put the metal first, and then you put the non-metal. Just a second. Sorry, I had to cough there. We're positive people, so we put the positive part of the ionic compound first, and then make sure you verify that when you write the formula that the total charge is 0. So if I put 2 potassiums together with a sulfur, there's my formula. Finally, when you write the formula, do not write any charges on it. The charges have neutralized. Don't include them. So if you do something like this, I'm going to put these in a different color. I'll put a big fat X through your answer. That's wrong, okay? So don't write the charges on your formula. When you've written the ionic formula, all the charges neutralize, and so you don't write them. The total charge is 0. So you just leave it 0. All right. Let's try one with a transition metal. Let's put these two together. I want you to apply the idea of balancing out the charges to get the ionic compound. So we're going to make rust out of iron with a 3+ charge and oxide with a 2- charge. What I want you to do is tell me how many of each thing do you need. And so you could just keep adding these as you need them. And then say, okay, do I have a charge here? Does that balance out? No. Do I need more? What do you need here? So add them in there, sum all the charges until you get a total that is 0. And I'll give you a hint. Think of the common denominator. All right, I'll give you a few minutes to think about that. Type the formula into the chat when you are done. And we'll go over the answer in just a bit. One more minute, we'll go over the answers. All right, let's show how we got the result. So, oops, let me get the red pen back here. So, if I combine these two together, then the result that I would get would be positive 3 and negative 2. And that's no good, right? I have too many positives, so I'm going to need more negative. So if I do this, how does this change? Now I have two O2 minuses, and now I have too many negatives. Well, that's no good. So now I need more positives, so I'm going to add another one of these in here. How does that change? Well, 3 positives make 6 positive. 6 positive and 4 negative is 2 positive. Oh no, that's even worse, but we can actually fix the problem by doing that. And now we have 0. I'm trying to make a giant check mark. I should really just do this. There you go. So, if I use these irons and these oxides, I would make an ionic compound with total charge 0. And so the formula would be Fe2O3. Very good. All right. So that's your task. You're going to have to figure out, by fiddling around with the ions, what compound forms. If I give you the if I give you the ions, like I did here, you just go straight to this process. If I give you elements, and I say what ionic compound would form, well, you're going to have to use the octet rule to figure out what ions you would eventually combine. Okay, so we have done this step. That was yesterday. Oops, I didn't actually do this part, though. There you go. So you may have to get to this step from the top. And in fact, that's what's going to go on the next slide here. Let me clear this so you can read that. That's not what I meant. Because I have 2 slides for you to do. Here's the first one. I want you to take these neutral elements and turn them into ionic compounds. Give me the correct formula of the formula unit, okay? And then once we've done that, we'll go to page 2, which is just the me giving you a bunch of different ionic compounds and you putting them together, okay? So we'll start with page 1. You can move on to page 2 if you finish, because you have the slides there, presumably. Go ahead and do these. I'll give you about 5 minutes. We'll go over the answers, then we'll put page 2 up, and then we'll take our break after we've done the answers for page 2. See you in a bit. How are we doing? Once you've got some formulas, go ahead and type them in the chat. And I'll go over the answer with you about 4 more minutes, 3 more minutes. Yeah, we'll try that. All right, 1 more minute. We'll go over the answers. All right. So let's go over the answers here. We'll take our break because we're about at that time. I'll just put 2 of these on the board at a time. So let's clear this out. Oops. That's not going to work. There we go. Okay, so for K and Br, we need to figure out what charges they adopt. So there are my 2 elements. So if I get rid of this electron, potassium gains a plus charge. And if I add an electron, bromine gains a minus charge. Hi, yeah, you're a cat. I'm busy. Maya just wants me to hug her all day. All right, so I have K plus and Br minus. How many of each do I need? Well, if I have a 1 plus and a 1 minus, those balance out pretty quickly. So the formula that we get is KBr. You're going to notice that the second one does more or less the same thing. Here's my calcium and here's my oxygen. So my calcium has 2 valence electrons, group 2. Oxygen has 6 valence electrons, group 16. We're going to get rid of these 2 to make an octet. We're going to add 2 to make an octet. And there you go. You're all set. Now for the next few, we have to start adding in extra atoms because the charges don't balance out conveniently. So let's look for magnesium here and chlorine. So there's what magnesium looks like. It's in group 2, it has 2 valence electrons. Chlorine is in group 17, it has 7 valence electrons. So I'm going to get rid of these 2 to make magnesium have an octet. I'm going to add 1 to give chlorine an octet. And if I add those together, I don't have a 0. So I need to modify the number of ions that I have here. Well, I have too much positive, so I'm going to add a negative in there. So we'll grab another Cl minus. And now it works, right? So my formula would be Mg, because there's only 1 of them. Cl2, because there's 2 of them. MgCl2. There you go. We can do the same thing for sodium and nitrogen. So here's my sodium. Here's my nitrogen. Sodium's in group 1, so it has 1 valence electron. Nitrogen is in group 15, so it has 5 valence electrons. So here's what we'll do. We'll get rid of 1 electron to make sodium look like that. There's its octet. Nitrogen needs 3 to make its octet. Oops, that didn't work. I just need more stuff. I need more positives to cancel out the excess negative. And since these come in 1s, I'm just going to put a bunch of them down, right? So now when I sum them together, I have 3 positive 1s and a 3 minus. There we go. So I'll sum them together. I got 3 sodiums and A3. I got a nitrogen, and there you go, Na3N. And then finally, this last one here. Oh, we're out of space. Well, I can go over here. If I mix aluminum and oxygen together and make an ionic compound, well, here's what aluminum looks like. Here's what oxygen looks like. Aluminum is in group 3, so it or 13 actually. So it has 3 valence electrons. Oxygen is in group 16, so it has 6 valence electrons. Okay, I gotta make octets. I gotta get rid of the electrons on aluminum. So we'll get rid of these 3. There's my aluminum. Oxygen wants to gain 2 to get its octet. And now I have too much positive, and this is basically the iron and oxygen example all over again, right? So if you go back and forth here, you're going to say, well, I need more negative. Now I need more positive. Now I need more negative. And when you get to this point, and you do the tally, you'll say, oh, okay, well, I have 6 positive, 2, 4, 6 negative. It's balanced. And so there's the formula. Al2O3. All right, so that's how we construct ionic compounds. When we get back from the break, I'm going to give you the second page of ionic compounds. That looks like this. So you can do that during the break if you really want to. Or, you know, be like a normal person and take a break. Go on, you've earned it. All right, I'll see you in a little bit. Alright, we're back. I'm going to turn the music down here, and then it's going to get real quiet because I'm going to give you some time to do these exercises on your own. So, I see some people have already started them, but applying the same principles that you did on the previous exercise, I want you to make ionic compounds out of these pairs. I'm throwing in transition metals in here. You don't have to worry about the octet rule for any of these because I've already given you the charges. So go ahead and do that. Make more ionic compound formulas. Tell me the formula units. We'll go over the answers in just a little bit. We'll do 2 more minutes on this one because this one has a little less work to do. All right, let's go over the answers here. I'm going to do them on this screen because I have enough space here. So here I have a positive 2 and a negative 1. I'm going to sum them sideways here. So this is no good. I need more negatives. So if I add a second one of these, then everything changes, like so. So if I have 2 negative 1s, I now have negative 2. So my formula would be BAI2. We just did one like this with aluminum and sulfur, and we had the same charges. So the only difference between the aluminum oxide and the aluminum sulfide one is you write a different letter. So you should get this for your answer. And then we also literally did this one on the previous slide. I don't know why I have that example twice. But the titanium one we can do. So I have a 4 plus and a 2 minus. And so when we sum those together, I have too many positives. So I need another O2 minus here. And when I do that, I have negative 2 is negative 4. There we go. TiO2. And then this last one, thankfully there's lots of space down here. So I have positive 5 and negative 3. Obviously that doesn't work out, right? I don't know why I did that sideways when I literally just set it up to do it this way. So I have too much positive, so I need to put another P3 minus in there. And when I do that, this becomes that. Now I have too much negative, so I need a positive, but these only come in chunks of 5, so this is just going to keep going back and forth and back and forth and back and forth as I add these together. So now I have positive 10 and negative 6. That doesn't work. That still doesn't work. Now I have negative 9. If I do it again, I'll need more positive. When does this end? And so let me just write down the correct answer. And we'll show you a little bit of a shortcut that helps you figure out when you have the right answer. So here's what you're supposed to have. And keep in mind, I am including these right here too, these ones, as part of it. So I have 3 vanadiums with 5 plus, so that's 15. And I have 5 phosphides with negative 3, so that's 15 also. And so the formula is V3P5. Now, how the heck did I get to that so quickly? And the answer is, well, if I have things that are in chunks of positive 5 and things that are in chunks of negative 3, and I have to balance them out, the easiest way to balance those out is to just multiply them together, right? What's 5 times 3? Well, 15, right? And you'll notice that, oh, that's where this number comes in. So if I put down enough 5 positives to get to 15 and enough 3 negatives to get to 15, I should have the formula. And this will almost always work when you look for common denominators. Or common multiples, I guess. The one or two places it doesn't work would be in this example right here. If I looked at titanium, and I said, well, I have positive 4 and negative 2, and I multiply those together, I would get 8. So I should have 2 titaniums and 4 oxygens to get 8. And you'll notice that this is not the same as what I got here by using this multiplier sort of idea. Well, if that happens, then just divide out any whole numbers that you get, and it'll be fine. So if I got Ti2O4 by saying, oh, everything can multiply to 8, and then I see, oh, well, both of these are divisible by 2, I could just divide them out. Because it turns out what ionic compounds are is what's known as an empirical formula. It's just a ratio of the positive part to the negative part. And so TiO2 and Ti2O4 are both the same thing. In a lattice, anyway, because it's just a ratio, right? The lattice is the whole entire thing. We're trying to find the formula unit. By definition, though, the formula unit is the smallest ratio. So the correct formula that we want is this one, and we don't want this one. So at some point, you will get to the level where you can just look at the formulas and multiply the numbers together and write down the formula on your own without having to do this piecewise, what are the charges sort of idea. And that's fine. That's totally fine. But do remember, you want the lowest common numbers, or you want the lowest possible numbers for your formula. All right. Now that we've done this in the forward direction, we need to go in the reverse direction. So I've given you ions to make a formula. Now I'm going to give you the formula, and I want you to tell me what ions are in it. Now, there's two ways to do this. The first is to look for group 1 elements and just, you know what element or what charges those ions make, right? Because they follow the octet rule. The second way involves transition metals and stuff, and requires you to solve for stuff. You can apply the second way to these examples, but you don't have to. So let's look at an example here. What ions were used to make this? Whatever the hell this is. Like, you've probably never seen cesium arsenide, right? Well, if arsenic is in group 15 and cesium is in group 1, what does that tell you about those things? Well, cesium would look like this, right? Before it became an ion. And arsenic would look like this before it became an ion, because it's in group 15, right? So how do I make them ions? Well, this is the ion that would form for cesium because it makes an octet. And then this would be the ion that forms for arsenic because it forms an octet. So there's your answer. The ions that were used to make this were cesium with a +1 and arsenic with a -3. So we have split the formula into ions. Now, if you have only group 1 through 8A elements, again, groups 1 and 2 or 13 through 18, this is easy. You can just figure out the octet rule. But sometimes you get transition metals or intertransition metals, and you can't do that. So then what you have to do is you have to problem solve. And so this is how you do that. How do I figure out what ions go into this compound? So let's write this down. I'll just go scroll up a little bit so that I'm working at the top of the screen here. So I have tin, and I don't know what charge it has. I'm going to just put a big question mark here. And I have oxygen, and I also have another oxygen. Now, as an ionic compound, my oxygens would look like this, right? There it is as a neutral. And then, when I fill in the octet rule, there it is as an ion. So each of these oxygens is -2. So remember, what do we know about the ions all added together? Well, the total charge equals 0, right? So if I have -4 here, what's got to go here, and thus must be this thing? Well, if the total charge is 0, it's got to be +4. So our tin ends up being +4. And you can check that by summing these two together. +4 and -4 make 0. And so for our formula SNO2, this was +4, and each of these was O2 minus. And there you go. That's how we break apart ionic compounds, is we do this sort of idea. Figure out what the charge of one thing is, and apply it to the other thing, because the total has to be 0. Now, what if you add multiple of something there? So I'm going to just pick a different example here. We'll do... Oh, I clicked off of the PowerPoint here. Let me just do that so that I can't do that. What if I had something like, say, that? What would the charges on the ions for this be? Well, let's split it into what it is. I've got chromium with a question mark. I got another chromium with a question mark. And I got 3 oxygens. And we know as an ionic compound they make -2, because we just did that above, yeah? Well, the total charge must be 0. How many negatives do we have? Well, we have -2, -4, -6. How much positive must we have? Well, it's got a counter -6, right? So this needs to be a total of +6 split among 2 things. So what must each of these be? Well, it's got to be half of what's available. And so then we can check. I put the 2 in the wrong spot. And there you go. You're all set. So that's how we split our ions from a formula to figure out what they are. Is you have to do a little bit of solving using the logic behind ionic compounds that the total charge is 0. Okay? All right, so I'm going to give you a few of these, and I want you to break them apart. I want you to tell me which ions are in these compounds. So aluminum and bromide mixed together to make AlBr3. If that's the ionic compound you make, what must the ions be based on the information that's there? You can either use the charges for all the elements that make the octets, or just solve for or figure out one and then solve for the other. It's up to you. Type your answers in the chat, and we'll go over the answers in about 5 minutes. All right, 2 more minutes. We'll go over the answers. Make sure to type your answer in the chat when you have got it. To the best of your ability, anyway. All right, let's go over the answers here. So, for number 1, I have aluminum and bromide. I know that bromine is in group 17, so it must form a -1 ion. And aluminum is in group 13 and must form a 3+ ion. And I can apply the same thing to calcium and chloride here. Chloride is also in group 17. Calcium's in group 2. And there you go. But it's these other ones where we have to start solving for stuff. So let's look at osmium here. So I've got osmium, and I don't know what its charge is. But I've got 4 oxygens, and I know oxygen has a charge of 2-. So if this is the negative total, what must the positive total be? Well, it must be +8. So that the total charge is 0. All right. What about rhenium and chloride? So I've got rhenium here, and I don't know what its charge is. But I know that Cl is always a -1. And I have 7 of them, and I got to write them all in. So what must rhenium be? Well, it's got to balance out the charge, right? There you go. And yes, these are real compounds that I looked up. For gold oxide, I've got 2 golds, but I don't know what their charges are. I've got 1 oxide. That should be a 2. Well, what must the total positive be? Well, this has got to be 2+, right? And it's split among 2 things, so each of these must be just 1+. Which I'm just going to write as plus. And there you go. And then following the same sort of idea over here, scandium, I got 3 of them. Don't know what they are. I've got 2 nitrogens, and we know what the charge on nitrogen is as an ion. We've worked with it a lot today. So each of these must be +2. There you go. So there's all your answers right there. All right, that's how we make and break ionic compounds. So this is actually a very important lesson, everything that we covered today. Make sure that you are aware of how to do this because we're going to be using these ideas so much through the quarter that I'm going to just assume that you know how to do this. This is the foundation for everything you're going to do in Unit 11, which is naming. It's also going to be very, very relevant to you when we're doing balanced equations, things like that. All right. The last ionic compounds that we're going to be making are ionic compounds that consist of polyatomic ions. These are the ions that I asked you to memorize way, way back when we started Unit 6, right? Now, we're not actually going to be really memorizing them because, again, online class, you could just have them listed. But being able to recognize them can save you time, and that's important. Polyatomic ions are just like regular ions. It's just that instead of having an ion that looks like this with a minus charge, you have an ion that looks like this with a bunch of atoms stuck in there and a charge attached to it. Now, ionic compounds don't care about the identity of the atoms because all we've been doing really is just whatever the thing is in there, put enough of those negatives with enough positives to make the ionic compound. So if I had sodium plus, regardless of whatever was in here, this is the formula that I would make, right? So polyatomic ions act like any other ion. You're just going to have some cluster of atoms in parentheses with a given charge. So let's look at some of those. Oh my goodness. There we go. So if I wanted to make something with calcium with a 2+ charge and phosphate, which is PO4 with a 3- charge, we would do the same thing that we did before. Just this PO4 is going to be our cluster for negative. Well, I have a +2 and a -3. Those do not add up to 0. So I can keep adding things until I have a balanced total charge. So now I have +6, -6. I can make the formula, and the formula I would get would be I have 3 calcium, so I'll write that. And then I have 2 phosphates, which I'll put in parentheses. And there you go. So with polyatomic ions, it's literally the same thing we've been doing. It's just that instead of writing only elements, now you're going to start putting things in parentheses if you have multiples of them. Note that you only need the parentheses if you have more than one. So if I only had 1 phosphate, I do not need the parentheses because I would not be writing a number after it. So the parentheses are only important if you have multiple of them. See this 2 here. Obviously, this is totally wrong because you don't have 42 oxygens here, so you do need parentheses for this instance. But if there was only 1, you would not write that number there, and thus you would not need it. All right. So I have the same exercise that we've been doing all day. Hooray. I want you to combine these ions at the top using my polyatomic ions that I've given you. And then I want you to break the ions at the bottom apart, looking for polyatomic ions. You're going to need to have that chart handy to find the polyatomic ions if you aren't aware of what they are or what their charges are. Because if you don't know what the charges are, you can't figure out what the transition metal charge is for the iron or the vanadium at the bottom. Okay, so go and refer to those. They're at the start of Unit 6 if you need them. I'll give you 5 minutes to do that. We'll go over the answers, and then we'll finish off Unit 9 because there's a little bit after this left. All right, 2 more minutes, and then we'll go over the answers. That's no good. Yeah, you couldn't hear me because I had the mute button. I'm sitting here talking to myself and doing all the examples. I feel like you can do the top ones on your own. I'll do these, but I'll walk through the bottom ones. Yeah, you should be able to hear me now. Sorry, that was my bad. Hopefully you can hear me now. I mean, it's showing that I am transmitting audio. All right. So for these bottom ones, you're going to have to look up these polyatomic ions so that you can find their charges. No, sometimes we have technical difficulties, and the difficulty is that I don't know how to click things. I just didn't click the button. I thought I did. So I apologize for that. We know that cyanide is Cn minus because it's up here. So if I got 3 of those, iron must be +3. And then what the heck is this? SO3 has a charge of 2 minus, and there are 2 potassiums that are positive. For the most part, you can usually figure out what the ions are in the context of the situation. This bottom one is actually quite difficult to do that. You really need to know what phosphate is, and phosphate has this 3- charge, and that will help you get to vanadium with a 5+. Vanadium often has a 5+ charge, it turns out, but not always. Not always. Just usually. All right, so that's how we do those types of problems. More or less the same exercise we've been doing all day. Balance the charges, add them up so that they total to 0, and that's how many of each part you need for the formula. Okay? So if you remember that, charges have to total 0, you can make ionic compounds and then split them apart. All right. That's all we're going to do for ionic compounds in this class. So that's a lot, but that's all we're going to do. There is more to it. We'll talk a little bit more detail about it in 161. Now, the last bit of Unit 9 is just, how do you know if something is ionic versus when it's not? And this is sort of my segue to Unit 10, which we're going to do, next week. So no quiz is going to be assigned this week because the next quiz is Units 9 and 10. And Unit 10 is real short. How do you know if something is covalent versus ionic? We have a little table for you. So we've already talked about this first one. We've got formula units versus molecules. Remember that ionic compounds form a lattice? And that lattice is formula units that you can copy and paste. But molecular covalent compounds are individual discrete entities that are just kind of hanging out independently. We talked about electron transfer for ionic compounds. You do not do electron transfer with covalent compounds. So instead, we're going to look at a different model where you share electrons. And then finally, we've talked a lot about how we need metals to give up their electrons and nonmetals to accept the electrons for the formation of the ionic bond. In covalent compounds, there are no metals. There are only nonmetals. I don't know why this gap is so much bigger on this one. That's weird. PowerPoint is weird. Now, there is one interesting exception that we're going to talk about, and that is when you have ammonium. All right. So if I am asking you, is it an ionic compound or is it covalent? Look for metals. If you see a metal, it's ionic. However, ammonium is very easy to overlook, and this is ammonium right here, because it only contains nonmetals, right? There's nitrogens and hydrogens. However, that said, it's a polyatomic ion, and all ions form ionic compounds. So if you see ammonium, the compound is ionic. All right. So on this last set of exercises, I'm going to just do these real quick for you. We're going to look for all the metals. So metal, 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 metal. So those are all ionic. But what else is ionic? If it contains ammonium, remember that ammonium is NH4+. So if you see NH4 in there, which we do here, these are ionic. Anything in green. The other ones, which we'll paint purple, these are molecular. Or, oops, sorry, that's not the term we're using here. They mean the same thing. It's just, I want to be consistent with your book. So these are covalent. Now, this strategy is going to be important for you when we get to naming compounds, because I'm going to just throw compound names at you with no further information of whether they are ionic or covalent, and it will be up to you to determine what they are and what the correct rule is to apply in Unit 11. So, the first thing you're going to want to ask when you look at an unknown compound is covalent or ionic. And once you've determined that, you'll know what to do with it. Okay? So remember this. It seems like it's trivial and that you don't really care, but it will be important later on. All right, I think that that's it for Unit 9, so we'll just do this. And we'll celebrate. Hooray! So, for tomorrow's lecture, we're going to talk a little bit about lab number 3. Lab number 3 is real easy, though. Lab number 3 is literally watch this video and make observations. It's just like lab number 1, but in a different context. And it deals with ionic compounds and properties that we didn't really get a chance to talk about in the lectures because they're things that you really more want to observe in the laboratory. So I gotta click this before my my monitor idles and turns off. So you will get to see that tomorrow. That'll probably take like 15 minutes. Then we'll do our Q&A. I don't expect that there are that many questions right now. Maybe on Unit 9 stuff. But yeah. So we'll have that. Tomorrow's lecture will probably be pretty short. Which is good because we just had an exam. We deserve a break, right? So see you tomorrow for that. Make sure you get quiz number 4 up and done. Deadline is tonight. Closes tomorrow. See you tomorrow.